Okay, so we're ready to continue on in Module 2. We are going to be finishing up our practice problems today. I'm going to click on those a little bit here. The last time we were together, we did 4.1 and 4.2. This evening, we're going to do 4.6, 4.7, and 4.11, which will then round everything out and prepare you for the homework problems that are coming up. So we'll discuss this at the end of our lecture this evening. And so I'm going to start by going to our Module 2 learning plan. I'm going to pull up our PowerPoint presentation, and we are going to continue, if you would, where we left off. I'm just going to zoom out a little bit here. So we got through displacement. We did example 1, example 2, and now we're ready for what is section 4.7. So I want to remind you that in this book, we do cover a lot of ground. We're going to be using it in each one of our modules throughout this course, but we don't cover each and every section in each and every chapter that we do. So this is one of those cases where we're going to skip over some things. And then we're going to be kind of landing on 4.7. Now, 4.7, you'll notice says limiting positions, graphical analysis. Like I've mentioned before, we're going to focus on drawing things out, getting the graphical analysis. I have the utmost confidence in you that through the other courses in our program, all the math and the proving out that you do in the physics classes and the statics and the strength of materials and the machine design elements, that this would just be another kind of repeat of that. So that's why we focus on the graphical to kind of get the ideas across, but then also, I don't want to say that's ever a waste of time, but we're not redundantly doing information. So we're always going to focus on graphical analysis. So really the sections that we usually skip over are the ones that are laying out, if you would, the math, the trig, the, sine and the cosine law applications. So limiting positions. Limiting positions are when we configure our mechanism so that we can see what the extents are of the output motion, okay? So when we do that, we call these the limiting positions. And what they're going to be is they're going to be the extreme positions of sometimes if it's the furthest point out and the closest point for where I'm going to use the slider as an example, okay? Or if we have something that's oscillating, what's the angle for which it's actually going to go through when it goes through its full motion for that mechanism? Now, when we talk about stroke is a very popular term that we use when we find the follower displacement, the total follower displacement from its furthest out position to its closest position on when we have linear motion. So stroke is always going to be a linear displacement, where another term that we're going to find is going to be throw is going to be the angular displacement. Now, if we take a peek at figure 425, that's at the top of page 88 in your book. I'm going to go under my camera here. It's right at the top. We have two examples of these limiting positions, okay? Limiting positions. So the first one on the top here is looking at a mechanism where we've got our input, which is a crank, for instance. Notice that the direction of rotation is clockwise, okay? And we have the crank going around. Now, they have three configurations here of our mechanism. The first configuration, which is going to be just a random position inside of what we call the cycle. The cycle is going to be when we make one full revolution on our crank and we get the full motion of all the other links in our mechanism. So this is a random place in our cycle. So they just drew link number 2, 3, and then 4 being the slider here. And you'll notice that here, this is the position of the slider, again, somewhere inside of that cycle. You'll notice that over to the right, its furthest position out, they have the placement of the slider in what they call C prime prime. And then they have another placement of the slider at C prime. These two extents represent that full motion of the slider when the crank goes all the way around 360 degrees. These are the limiting positions, the furthest extreme out and the furthest extreme in. The difference between those two is called stroke. Stroke is always that linear displacement, that total linear displacement of a member that is going to be moving in a linear fashion, okay? The other one that we see down here is when we have a mechanism that has a crank on the input, but now instead of a slider, it has a link that oscillates back and forth, okay? And so here, our final or our output link, you'll notice has three positions. The first one is within the confines of the total cycle. And then the second one is going to be that closest position, C prime prime. And then this one's C prime and this one's C prime prime. The difference between those two on the outside are the extreme positions. But this time, that link is limited to moving only as an oscillator because at point D, the point is going to rotate about a fixed center. So in this case, the total displacement is called the throw. And the throw is going to be measured with an angular displacement. So like the total angle between those two extreme positions. Now, why would you think this would be important to us? Why would this be something that we would want to know from a designer standpoint? Tyler.
Basically, it kind of limits to say how we gotta make sure, hey, how much space does this need to fully operate?
Perfect. Yes. So Tyler answered that question with how much space do we need for this to operate? And many times it's not unlimited, right? The space that you have isn't unlimited. So you have to make sure that it fits within the confines of, if you would, a box. And by going through this process and laying out the mechanism really before any details are worried about, this gives us that opportunity to just make sure that everything fits within the confines of, right? What's another reason why we may want to know the answer to this? In either case, whether it's a slider or if it's an oscillator. Timing, yes, that might be an issue that we want to know, like how long does it take to go through that cycle when it's going to be moving back and forth? Yes, timing would be another great reason why we want to lay that out. I'm thinking of one other. What about function? Just checking to make sure that how you have, the length of these different links are going to dictate how far this might go out. Is that stroke enough for the function of your element? Or is the oscillating, is the throw enough for what the final function is for that particular mechanism? So space, timing, just function in general, like am I covering what I need to? Those are reasons why we want to make sure that we understand the extent of the motion of not only the input, but also the output, and what's happening there. So the first example we're going to be looking at is example 4.6, okay? And for this problem, we're going to be determining the limiting positions or the stroke of this blade mechanism for this reciprocating saw. So what it says here, they want us to determine the configurations of the mechanism that places the saw blade in its limiting positions, okay? So you'll notice here that they're giving us an overall drawing, okay, of the elements. So at the center of the circle here, this is like one of those little flywheels that are probably a motor is in back of this. We just don't see it in this view, but the center of the motion, the rotational motion, is going to be right here at the middle. So it's going to rotate this around. We connect then, I'm going to call it a connecting link that is then going to connect to the blade, which is just going to move up and down. Okay, so that's going to be a slider at this point. Okay, so to represent the flywheel, remember, we don't draw the circle. We're just going to draw from the center of rotation to the point that it connects to as just a radius, okay? And then what we're going to do is then we're going to add, based on the dimensions we have here. One dimension that they are not showing is, in this position, what is the angle that this is at? I'm going to draw mine at a 45-degree angle from horizontal, just so you know. I don't know exactly what it is, but that looks about what it's going to be. That's not super important at this point. We just want to get the kinematic diagram laid out, and then we're going to be moving it to its furthest point down and its furthest point up to get those limiting positions. So what I'm going to do is I am going to stop the recording here briefly. And I'm going to open up my AutoCAD and we're going to draw the kinematic diagram, and then we'll be back to kind of start from that point. So I'm going to let everybody work independently on their kinematic diagram, getting this in place. I'm going to do mine at the same time in the background here. And then I'll resume the recording once we're kind of at that point and ready to move things around. Now, as we look at our diagram, I put the dimensions for each one of the elements here that's given in the illustration. This is only to prove a point where when you start your diagram, it is always good to confirm all of the sizes that they're given, because if you don't have it set up correctly, or if it's off by just a little bit, your results obviously are going to be off as well. And sometimes when you get to the end, you're like, it didn't quite come out. It's usually here somewhere. So some way, somehow, do a double check on your dimensions before you go, if you would, to the next step. And that's all that I have here. I'm actually going to get rid of them now. And I usually do this all the time still, just as a quick confirmation, because it's so easy, even in CAD, to not put the right dimension in place and then not really realize it until you don't get a right answer. Okay. So now that I have my initial diagram done, I always want to do a quick check. Now, the book doesn't require us to do this in this example, so I'm not going to require it on the practice problem, but let's do our mobility calculation really quickly, just to be sure that we have what we're expecting. Now, in this case, we're going to be getting the numbers of degrees of freedom is going to be a 1, okay? This is a 4-bar mechanism. Now, I didn't put all of the labels for the links in place just to save space here. We have got a kind of a confined mechanism. So I just want to be sure that I have enough space to move things around, and I'll add these in later. But I have number 1 is my frame. Number 2 is my crank. Number 3 is going to be the connecting rod. Guys in the back, I'm just want to make sure everybody can hear what I'm saying. Connecting rod. And then number 4 is going to be my slider. So this is 4 links. So if we go underneath and we calculate the mobility, we know that our equation is going to be F is equal to 3 times n minus 1 minus 2 JP. So our 3 for our number of links is going to go right here. Okay. And then our number of primary joints, if we go back over here, we're going to have joint A, B, C, and don't forget there's one more. Again, I didn't put it in here just yet, just for the sake of the layout. I'm going to have a D here as well. So there are 4 primary joints. So back underneath here, this is going to be 2 times 4. So if I take and I do this calculation, I'm going to notice, oh no, this is 4. I'm so sorry. I was thinking 3. I know I have to get 3 here. So this is going to be 3 in here times 3 is going to be 9 minus 8. So my F is going to be 1. Again, not required for this problem, but it just means that we only need to do one thing, and that's going to be rotating our crank in order to get this reciprocating saw to go up and down. Okay. So, so it really just confirms that we have the correct number of links and joints identified in our diagram. Okay. So now that we are here, we are ready to take it to that next step to find the limiting positions. So we want to find out for link number 4 here, how far is it going to go down? That's where we're going to start first. Now, to do that, we are going to use the lengths of these 2 links, link number 2 and link number 3. And the place that it's going to be its furthest down is when, kind of following my cursor here, these 2 are going to be straight in line with one another. And their radius then is going to cross over that vertical line of action. So to find out where that's going to be, we're simply going to add the length of link number 2 and link number 3. Okay, link number 2 is going to be my crank, 3 is going to be my connecting rod. If we go underneath our camera and we look over on page 89, okay, so what we drew right now is just the overall kinematic diagram. And over on the right here, they do a nice job of laying out and showing us how we get these radiuses. So to get the furthest point down along that vertical line of action for that slider, we're going to take capital L2. That's the length of link number 2. And we're going to add the length of link number 3. Okay, so we're adding how long 2 is and how long 3 is. And we're going to strike that arc with the center being at A. So going back to AutoCAD, I am going to go up to my 0 layer. I'm going to create a circle center radius. My center is going to be at point A here, okay? And its radius is going to be adding together 0.5 and 1.75. 0.5 is the length of the crank, link number 2, and 1.75 is the length of link number 3, the connecting link. So what is that number? If I take 0.5 plus 1.75. 2.25. Yes, so 2 1/4. So I'm going to put in 2.25 as my radius. Notice that it crosses the line of action of my slider right down at that point right there. Okay, that's going to be the new position of point C. So my slider is going to physically move down. So what I'm going to do is I am now going to copy this slider. Yes.
My circle is much smaller than yours.
I don't know. You got to check the dimension.
2.25 for diameter?
Nope. Nope. What would it be? Look at the construction. The center is at A, and I need to add those two lengths together. That's not a diameter. That's a what? Radius. Yes. I don't think I did. It was circle center radius is what we use. That's okay. That's okay. So now we're going to move this down. And we're going to go down from that center to the intersection that's created right there. Make sure you use your object snaps. And then now we want to put this in a different line type and color so that we can see that it is a different one. Now, from the last time we were together, we did add object 2 to our line types. So that's going to be the green hidden. Okay. So that's going to be the new position. And then we are going to draw a line going directly from joint A all the way down to the new position of C. This new position of C, I'm going to copy C down, and that is going to be C prime. So C is just kind of an intermediate inside the cycle point. C prime is going to be the furthest down point. Okay. So this is one of our extreme positions. Additionally, B moved, right? Now I left in this radius of a 1/2 inch for the circle there. So at the intersection, I would add my pin connection right there. And that is going to be the new position of B, which is going to be called B prime. What was I told? Yeah, the D would be over here, but I didn't put it in because I would be moving it around. So I'm just going to wait till after I get my positions here. Yes, there is a D. So there's 4 links and 4 joints for the mobility equation. Other questions? Okay, so this is the position now. You want to put in anything that moved. B moved, so we've got a B prime, and C moved. So we've got a C prime. A didn't move. D is just the joint between the slider and the vertical wall here. And so it doesn't change. It's going to continue to keep it constrained. So the only two that change are B and C. Okay. So this is the furthest down position. Now what we want to do is we want to find what's the furthest up position. So if we go back underneath our camera here, you're going to notice that we see the furthest up position, C prime prime, and that is going to be a radius where we take the length of link number 3 and we subtract link number 2, because what's going to happen is as it comes around, it's going to be overlapped here, okay? So we're going to take 1.75 minus a half an inch. What's that number? 1.75 minus 0.5. 1.25 sounds correct. So now we're going to do a circle center radius. Starting its base position or its center is going to be at A, and then its radius is going to be 1.25. And now it's going to cross right here on our line of action. Okay. Now I only have at this point 2 object lines. I have my white and I have my green. So what I'm going to do is I'm going to add a new layer. So I have to go to layer properties. I'm going to click on my object 2, hit enter, and I'm just going to change the color of that one. Remember that had the hidden line type on it, which I do want. And I'm just going to change it to cyan. So I'll have green and cyan. And then now I am going to put my, I called it, what did I call it? Did I not, I don't think I changed the name of it. Let me go back in. Oh, sorry. I didn't change the name of it. So I want to rename that layer. Object 3. There we go. And now when I go out and I look underneath, it should be, yep, at the bottom where I want it to be. Okay, so I've got object 3 on here. And what I'm going to do is I am going to draw my line from A to the intersection that was just created between the line of action and that 1.25 radius. Now, what I also need to do is I need to extend this line until in the back side here, it goes to the backside of the radius that is for link number 2. So I am going to use my extend function, and it's going to extend first to that radius and then to that radius. So you have to click it twice. And then now that's the location of the backside of where B prime prime is going to be. They overlap. Okay. So now I'm going to copy from the center here to the intersection. Where is it? Intersection. There we go. Okay. And then that is going to be B prime prime. Yes, Jacob.
Gray line, that's intersecting your the 1.25 circle and then your 1 over vertical line, correct?
Yeah. Mm-hmm. Another place you can look to if you want to is underneath here. You're going to see that this right here is that L3, the 1.75 minus the ½ inch. Okay. Yeah. And then my C prime prime is going to be up at this location. And I'm going to get rid of my construction lines that I won't need here anymore. But up, and then I'm going to move. Should be my last one. To the intersection. There we go. Now I have everything where it needs to go, so I'm going to get rid of the construction lines that I don't need. There we go. Kind of cleans it up a little bit for me. And then now I can put in place where they fit the labels that I still need to add. So I'm going to move my A hoping it'll fit right in there. It does. Then I'm going to move my number 2 be there. Gonna move my number 3 to be here. And then I'm gonna move number 4 to be here. And then I'm gonna move D. Looks like it'll fit like there. Okay. So now what this shows me is it shows the extreme positions, C prime prime all the way up, C prime all the way down of my reciprocating saw so I can see what the total travel is. Excuse me. Okay. Now, to see what that total travel is, I need to determine how long it is. What can I do now to determine that length? Measure it. Okay. How am I going to measure it? Put a dimension in. Right. Exactly. I'm going to put a dimension in. So I'm going to go to my notes, do a linear dimension from the center of the top to the center of the bottom, from C prime prime to C prime. And my value is 1.2656. Now, I need to move this around, my C prime prime and my C prime, so that they are not overlapping. When you hand this in, I know it's layout work, but remember, you're handing in to tell me the answer to a problem. Move things around so they're not overlapping. Move things around so they're easily understood. I don't want you to put a dimension and have it going through another label. Does that make sense? I know this isn't, you know, a drawing that you're going to be sending out to the shop floor to be made, but yet you are handing it in for an assignment. So make sure that your labels and things, you know, are easily read and make sense. So the answer here is the stroke, or the total difference between those extreme positions, is 1.2656. If we go underneath and we look at the screenshot, if you would, which is just below those on page 89, you're going to notice that they also got a total stroke of 1.2656, which is exactly what we got. Now, if you got something different, okay, then chances are, if we go back to AutoCAD, when you laid out the original diagram, something might be off. And that's why it's important to check your dimensions. And that's something you'll have to troubleshoot then during lab or something. And I can certainly, you know, take a peek and look later, but that's usually where the issue lies. Okay. So any questions so far on this one? Okay. Now, what you want to do is you want to go over and you want to find your document that you started where you did the first 2 practice problems for Module 2. So I'm going to go to my Module 2 practice problems. And I'm just going to pull up my Word document here. And what I did was, earlier today, I added my illustration for example 4.6. Okay, so you're going to notice here that this is the illustration with the dimension for that overall stroke. So you want to add in the screenshot. You do not need to do the mobility equation or the calculation here because the question or the problem is not asking us for it. Okay. And then once you have that in place, then that's what you add for the practice problem for example 4.6. Any questions? All right. Okay. If not, then what I'm going to do is I'm going to stop this recording here.